In the first Varimos project I showed you just like some seconds ago, I used process parameters as variables. In this project, it's the same part, it's the same quality features I'm going for, but the variables are different. The variables are, as you can see here, wall thicknesses. So it's the first variable I defined is the wall thickness of those 3 ribs here, as you can see here, are highlighted in purple. The second variable is the wall thickness of like the bottom of the part. So in this example, I changed every wall thickness I could like basically change. This is not always possible like in reality, but just for demonstration issues or purposes, that's what I did here. And I defined as a span, I told Varimos that it's allowed to change the wall thicknesses by plus minus 25%. You can do this like in a relative way. What you could also say, change the wall thickness maybe by plus minus 0.3 millimeters. This is also possible. And well, I'm changing the bottom of the part. I'm changing the wall thicknesses of those 2 ribs as one variable, and the wall thickness of this rib here in the middle is the next variable, and then the last variable is the wall thickness of those 2 ribs down here. So it's basically 5 variables, but in a geometric way, not like in the process parameter way as we've seen before. And then if you run through all those different simulations according to the DOE plan, which result out of those 5 variables, we could also open like this Varimos cockpit we opened for the project before, and this looks then like this. You see here the variables. It's the walls I changed, the wall thicknesses, and you see the wall thicknesses are already well defined a certain way. So 3 of those wall thicknesses are reduced. One is more or less the same as it was before, and one wall thickness of the outer and inner long side walls, so to say, are increased. And then you can see that you're able to get how much is it? I think 8 out of those 11 geometric quality features within tolerance. And you can also see how a wall thickness of a certain area just like influences your warpage issues. And you can see this is a really drastic influence. It's way larger than it was with the process parameters. So, and if you set up a simulation with the wall thickness distribution as it's shown here, as some kind of verification simulation, so to say, we can compare the warpage again. And this is what you can see here. So the warpage in the initial simulation was 0.3 millimeters. And when optimizing wall thicknesses, we can reduce this to 0.18 millimeters. And looking at the Z warpage is a reduction of up to 70% of the warpage. And well, this might be a very drastic example in which I changed everything I basically could change. This is not always possible in reality, and it's not always like those minus 50 and minus 70%, but just to give you an idea what can be possible in general when using like geometric variations. So this is as a last slide. Oh no, it's not the last. It's like the second last slide. The way we think of working with CADMOULD and Varimos. So basically, as I already told you and I already showed you that like the first initial design hypothesis with the CADMOULD, what I showed you in the very first simulation. Then if you see there's a problem, you start by varying injection molding parameters and just check if that's okay, that that's enough to build the mold, or if that's still not okay. Then you can think of changing or tweaking the geometry, the wall thicknesses, maybe also like gating diameters or gating positions. I did not show this in here, but this is also possible, and review this again. And if that's still not helping, it's still not okay, you can think of like mold compensations. And if nothing really is working, you then need some kind of fundamental change. And yeah, this is the last slide. This is a customer of ours who was simulating with CADMOULD, like I think 8 or 9 months ago. He did not use Varimos. Well, now he does, but back then he didn't. And he had a rather complex mold he was trying to build, and he had to run 20 different simulations, like in series, to get up to the point when he thought, okay, this is good enough for me. This took him about 200 hours, which is basically like in Germany, when you're working like 40 hours a week, it should be more or less a month of working hours. And those 10 to 12 hours are not, the simulations took longer than they did here. It wasn't just like 12 minutes. But these 10 to 12 hours per simulation also include like talking about and discussing results and thinking about like things you can change, or working with colleagues, co-workers, and so on. And this took him, all in all, about 200 hours. And then he heard of Varimos, and we basically did the same. We set up the very first Varimos project, as I showed you in here. And then we had, I think it was like 16 simulations, and we've computed them in parallel on a 6-core CPU, I think. And this took a little more than 1 day, just simulating nonstop on the PC. And then we analyzed those results and came up with a solution which was a little better than the one thing he came up with. So it could even be improved a little bit, not that much, but it could be a bit improved a little bit, and by just using a fraction of the time he was putting in that like before. Well, it's a very drastic example of how much time you can save when using Varimos, because basically always when you're simulating, you're analyzing certain results, and you try to come up with like things you can change or you want to change. And if you're doing so, you can always use Varimos, because you, as soon as you start at looking at different results and want to improve something, you can define this as a quality feature and think of certain variables you want to change, and then use the variant analysis basically. So it's not limited, or it's not only meant for very complex projects, or very big projects. Can be used like basically at any time.